All right, people, I'm going to try to knock out Chapter 3 in one single video. So I'm going to go a little bit quick, but it's all pretty easy stuff. We've actually covered a lot of it before. So let's talk about how you know what you have. Like, what am I talking about? Like, if you're holding a piece of matter, like, how would you know if it's plastic or wood or what? Take a second, think, ponder. All right. So the actual answer is it's the chemical and physical properties. What it looks like, the density, how it conducts heat, electricity, all that stuff. That tells us what something is. And don't forget about intensive versus extensive. So intensive means it's independent of how much you have. Extensive depends on how much stuff you have. So mass would be an extensive property. Color would be an intensive property. Let's cruise over the states of matter again. So solids, liquids, gas, those are the ones we're going to care about. So with a solid, your particles are all packed together tightly. They're not really moving. They vibrate in place, but they're not going anywhere. You can't compress a solid very much, if at all. Pretty much the same thing with a liquid. The liquid, the particles are in contact with each other. They're really squished together, but they are moving. They flow past each other. But there's not a whole lot of compression available with a liquid either. Gas, you have the particles all over the place, really far apart. All right, so lots of availability to compress there. So solids, liquid, and gas. Let's get to something new. So that's all stuff I think we've covered before. The law of conservation of mass. There's nothing on this slide, and there's not going to be, because I just kind of tell you what it is. So the law of conservation of mass says that in a chemical reaction, mass is conserved. That means it's not created or destroyed. So the total mass of all of your reactants equals the total mass of all the products, plus the mass of any leftover reactant. So a lot of times, you're going to have some reactant left over unless you have a perfect mixture of the reactants where you have exactly enough of one thing to react with the exact amount of the other stuff that you have. All right, so that's the deal with the conservation of mass. So basically, matter isn't created or destroyed in a chemical reaction. All right, how is a mixture different than a pure substance? All right, so pure substance, really hard to separate. You can separate it, but it's kind of tricky to do it. Except for water. Water is actually pretty darn easy, and I'm probably going to show you how to do that this summer. Anyhow, a mixture can be separated easy, and so I'm going to show you a bunch of different ways of separating mixtures in the lab. So first way here, we got filtration. All right, good way to separate solids from liquids. There's going to be a little piece of filter paper that goes up in this funnel. You got a little rubber stopper here to kind of seal this in here. This is usually connected to a vacuum line, or sometimes there's like a water aspiration thing. If you go into a chemistry lab, a lot of time on the sinks, you see the faucet sticking out, and you see this weird spout kind of sticking off the side. If you plug this onto there, it actually creates a vacuum when you turn the water on. And so it pulls a vacuum. It'll suck all the liquid down through here, leaving all your solid up there. This is called the lead donut because it's really heavy. It keeps this thing in place because these big rubber tubes are kind of unruly and your stuff will get flung all over the place unless you have it weighted down. So that's what the lead donut's for. We also have distillation. All right, so distillation, you've probably seen that in one of the videos I've had you watch now. But this is good for separating things that have different boiling points. All right, so you can separate a solid and a liquid. So salt water, if I put salt water in here and I heated it up, right, the water is going to boil off. It'll all collect over here, and this will all be left with the salt. But it's also really good for separating two different liquids, like alcohol and water. Those mix together infinitely. There's no saturation point to that. So, but alcohol has a lower boiling point. So when you heat this up, the alcohol is going to boil off first, and so you collect the alcohol over here, leaving the water back over here. Crystals. Crystallization is another way to purify something. So when crystals form, they tend to leave out the impurities. So that's kind of cool. Take a look at this picture. It looks a little funky. Like, it's a test tube. Yeah, What's odd about this picture? What's unusual? You see a bunch of crystals, but they're on the outside. They got there by deposition. So sometimes you can sublime something and then have it deposit on a cold finger as a way of purifying it. Iodine is something that we can do this with pretty easily. You take iodine or something that has iodine in it and you heat it up, and the iodine will go from solid right to a gas, turns into this nice purple cloud of vapor. And if you take a test tube with ice in it or something cold inside of it and place it into that cloud, that vapor will condense, deposit right onto that test tube and form crystals. All right, last one here. This one's actually really important. I'm not going to go over all the different types because I want to keep this video pretty short, but this is chromatography. So there's lots of different types of chromatography, but I'll just tell you about paper chromatography or thin layer chromatography. So TLC, that's what you see right here. This is where you have a plate, or you can use a piece of paper to do this. In chromatography, there's a mobile phase and there's a stationary phase. So something's moving and something's staying put. The solvent is the thing that is moving. It's your mobile phase. So if you put a dot, that's basically a mixture of stuff, onto this plate, and then you stick this plate down into a solvent, right? You don't want to like dunk the whole thing in here, but like just put the very end of this thing into a solvent. That solvent's going to creep up this plate. That's capillary action. So if you've ever accidentally had a napkin or something go into a little bit of water, you see how like it sucks the water all the way through that napkin? It's doing the same thing here. And you can see like all the way up here, this is called the solvent front. So as this solvent front moves across your stuff, the different components of your mixture are either going to want to stay stuck to the plate, or they're going to want to move along with the solvent. So the more they like the solvent, the more they move along with the solvent. The more they like the plate, the more they stay put. So you can see in this mixture here, there's 3 components. There's like this red stuff, blue stuff, and yellow stuff. The red stuff liked to stay put the most. The thing that liked the solvent the most was this yellow component, and then this blue stuff's kind of in the middle. And in the actual lab, what you can do if you really wanted to like isolate this further is you could take a little spatula and scrape off this red stuff. Like literally just scrape it off the plate, and then you've got that red stuff that you can. Then you probably actually have to separate it from the silica gel or whatever this plate is, but you can get it. All right, let's keep going. Keep rocking along. Ooh, how are elements and compounds different? Well, a compound is made up of one or more elements, and all of our elements are listed on the periodic table. Yeehaw, right here. This is gonna be your new friend. So we have a whole entire chapter dedicated to it, but I do want to say just to kind of introduce you, like the columns here, the vertical columns are called groups, and the horizontal rows, those are the periods. Some of these groups have names. We'll go over those later on. There's blocks in the table, all this cool stuff. So we're going to go over this a lot later on, but just right now, if you've never actually played around with one of these, go Google one, or actually I have one on Canvas for you guys to see. But take a peek, start to familiarize yourself with the different symbols and the different element names. All right. Couple more slides here and this chapter's done. It's a really short one. All right, so there's the law of definite proportions. So the law of definite proportions says that compounds contain the exact same proportions regardless of sample size or where it came from. So what this means is, like, if we do percent mass on water, for example, if I do the percent mass on water, water's made up of hydrogen and oxygen. It's 88.8% oxygen and 11.2% hydrogen. Every single time, right? It doesn't matter where that water came from. It's exactly the same. It doesn't vary, right? It has the same exact proportions. So that's why we have this law of definite proportions, all right? So it's not like you go someplace and, ooh, this stuff is 12% hydrogen. No, it's always 11.2 to 88.8. It's exactly what it is, and it does not change. There's another important law here. It's the law of multiple proportions. This one's a little weird. So I'm going to tell you some numbers and write them down if you have to let this sink in. But okay, so what it says here is when multiple compounds are formed between two elements, the ratios of the masses of each element in each compound will be whole number multiples of each other. Okay, what in the world does that mean? All right. So, for example, carbon and oxygen. There's multiple compounds made up of carbon and oxygen. So for one of these compounds, let's call it compound X. For every gram of carbon, there's 1.33 grams of oxygen. All right. For this second compound, we'll call it compound Y. Right. For every gram of carbon in compound Y, there's 2.66 grams of oxygen. So think of those numbers really quick. 1.33, 2.66. There's exactly twice as much oxygen in compound Y as there was in compound X. And there's another example. So let's talk about nitrogen and oxygen. So there's 3 different compounds made up of nitrogen and oxygen that I'm going to tell you about. Let's call them A, B, and C. Compound A, for every gram of oxygen, there's 1.7500 grams of nitrogen. For compound B, for every gram of oxygen, there's 0.8750 grams of nitrogen. And for compound C, for every gram of oxygen, there's 0.4375 grams of nitrogen. Now, if you have those numbers written down in front of you, just look at them, and you're going to start saying, hey, wait, this one's twice as big as that one, or this one's 4 times as big as that one. It's That's what this law is saying. Is that when you have multiple compounds formed between two elements, the ratios of those masses are whole number multiples of each other. So why are these laws important? These laws are telling us that there are building blocks of matter and that there is some smallest amount of matter that you can have. And those things are called atoms. And that's what we're going to cover in the next chapter. Holy cow, I actually got this done in just about 10 minutes. So really quick chapter. Next chapter, we're going to go into atoms and all that fun stuff. All right, see you then.